Life on Earth is dependent on temperature, but it's not really clear what is the lower temperature limit and what factors determine that. But it is generally assumed that the flexibility and the stability of the molecules determine these limits. So, why would that be the reason? Because when the temperature goes down, the molecules lose the kinetic energy and they become so stiff and they cannot carry out the normal physiological functions. So, if we compare the molecules at low temperature, in the meaning of flexibility, it will be like the Easter Island statues compared to Michael Jackson. So in order to understand these functions, we have selected the muscle because it's constantly at the move, and these proteins are a very good example. So we have chosen tropomyosin, which is a regulatory protein, and we want to understand how tropomyosin is capable of maintaining its flexibility at lower temperatures. So in order to do that, we have selected Atlantic salmon because it lives in near zero temperatures year round, and the other thing, I can easily get the salmon muscles from the supermarket. So what we do here, we compare the Atlantic salmon tropomyosin to the rabbit. Of the tropomyosin, there are 284 amino acids, but there are only 20 differences. Out of that, there's only one charge substitution. So when there's a charge substitution, we know there's a stronger interaction. So what do we do here? We have taken the salmon tropomyosin and has introduced the rabbit charge substitution into that. And then we are going to look at the flexibility and the stability of the molecule in terms of chemical stability and the thermal stability. So what is the relationship between the flexibility and the stability? If a molecule is so flexible, what happens? It reveals all the digestion sites, so the enzymes can easily break down the molecule. And also, when this becomes so flexible, we need less heat to break down the molecule. So that's the relationship between the flexibility and the stability. So I have compared the two tropomyosin, which is a salmon, and the salmon with the rabbit charge substitution. But we could see that when the charge substitution is there, as the diagram shows, when we introduce the enzymes, it easily digests. It is so resistant, whereas the other one is easily digested. So this has given a flexibility to the salmon tropomyosin when the charge is not there. And also, I need less heat to break down the molecule which doesn't have the charge substitution. So what does this mean? Simply that with this one charge substitution, it has given much more flexibility to the salmon tropomyosin. So now this molecule can carry out its function at the low temperature. So this really means these differences really matter for the life processes. Thank you.